So these are the two models that we built yesterday to introduce stereochemistry. And you can see that they are looking almost the same and they have all the same atoms, but the way that they're actually attached to each other is also the same, but the three-dimensional structure is not. And why this matters is that in biochemistry, these three could bond somewhere that fits these three atoms, but it does not fit these three. And this is just the simplified model that we use to introduce the topic. But if you look into the actual lemur box, you can actually see the two different forms of a drug that was produced, I believe in the early 1900s, called thalidomide. And one form of this drug was actually able to help lessen the effects of morning sickness, so it was taken by pregnant women. The tragedy of thalidomide is that the other form would cause birth defects, which was especially bad since the people taking it were all pregnant. If we look in the model though, we can, as a brief reminder, the reds are oxygens, the whites are hydrogens, the grays are going to be your carbons, and the blue is your nitrogen. You can actually see the nitrogen center, or the chiral center, over... how do I move this? Over here, you have your four different parts attached to it. So again, these ring structures look almost the same, but the way that this extra ring over here is attached is different. So it's actually the same thing as this one, but just a much more complex example that I didn't want to have to build out of these. Alright class, so yesterday we built our tetrahedrals, and I told you to build them with all the same molecules and then find someone who has a different molecule, which was very interesting because they're all the same atoms going together. And people were a little confused, which is normal. But as you look at them, they're actually quite different. Again, the mirror images are the same, but they're actually not the same molecule, which has tons of applications in how they actually function in the body. So this is basically an example of stereochemistry, where all the atoms are the same and their way that they're attached to each other, the bonding order is the same, but the actual three-dimensional structure is different, which is what we were studying yesterday. Anybody got any questions they want to ask about? All right, how about this one? Why are we studying this? So, why is stereochemistry important? Are there any historical references where stereochem was either very useful or very harmful?
Absolutely. The thalidomide tragedy is a prime historical example. In the 1950s, thalidomide was prescribed to pregnant women for morning sickness. One stereoisomer was effective, but its mirror image caused severe birth defects. This disaster led to stricter drug testing and approval processes. On the positive side, Louis Pasteur's work on tartaric acid stereoisomers in 1848 laid the foundation for modern stereochemistry, revolutionizing our understanding of molecular structures.
Awesome. Anybody got anything they want to ask?
Oh, I do actually.
All right, I'm pushing it. Go for it.
Are there any drugs that benefit from both the mirrored and non-mirrored version of it in different ways?
Interesting question. Yes, there are drugs that benefit from both stereoisomers, though it's less common. One example is ibuprofen. This enantiomer is the active pain reliever, while the R enantiomer is inactive. However, in the body, the R form can slowly convert to the S form, prolonging the drug's effect. This is why ibuprofen is often sold as a racemic mixture containing both forms, rather than just the activist form.
How do we separate the two enantiomers from each other if they're both produced at the same time?
Separating enantiomers, mirror image molecules, is called resolution. Common methods include 1. Chromatography, using chiral stationary phases that interact differently with each enantiomer. 2. Crystallization, forming diastereomeric salts that crystallize at different rates. 3. Kinetic resolution, exploiting different reaction rates of enantiomers with a chiral region. 4. Enzymatic resolution, using enzymes that selectively react with one enantiomer. These techniques are crucial in pharmaceutical production and research to isolate the desired enantiomer.
I'll just say that during my year for it, it was hard to tell how the different models were made, since we're kind of just looking at the same image and we're just saying that it's different, and it's hard to tell generally. But it actually helps to visualize how it is different, which was kind of neat.
I agree. I think this is a way to really condense a lot of other websites and ways to learn into one simple thing. I like it a lot. I think it has a lot of potential.
Like currently taking chemistry, we haven't really gotten to this point yet, but I see it as something that's going to be really helpful in learning this subject in the future. So I'm really looking forward to this technology being used in classrooms.
Yeah, it definitely helps to like visualize stuff a lot easier. Just like seeing it 3D and actually there, it's a lot easier to like understand it.
Cool. Yeah, Michael, as a teacher, what do you think about the tool?
Well, first of all, I just think it's awesome because I want there to be holograms, and that enough is convincing to me. But what I really think is useful is actually a lot of time in education when we talk about AI, it always comes up in like a negative sense of like, oh, people are just copying their essays or getting their answers. And like, first of all, like, what's wrong with people getting answers? If your entire thing is just answers, maybe we're not teaching it correctly. And I think that any sort of, good future for humanity involves people becoming more tech literate and figuring out how to utilize this technology to get past just the basic barriers of entry of just the knowledge part, which, obviously that's a huge part.
Yeah.
And it is important to know things. But having, AI in the classroom as a hologram that we can actually interact with helps accelerate the rate at which we can go and try to close that kind of basic knowledge gap, and then we can actually focus on like much more interesting applications of what's happening. And then a lot of the time, especially with chemistry, it's always a struggle of, so chemistry, we can see the effects of it, and nowadays we do have some images of atoms that we can see, but they mainly look like blobs to me, at the very least. And being able to see the world that you can't, the hidden world that you can't really see, is what I've been trying to teach for the past decade. And so being able to blow it up or shrink it and revolve it and make it into a three-dimensional thing that people can actually easily access and call upon is quite powerful.
Awesome. Thank you so much.